All right, just like the last video, what's the challenge? The challenge is to rewrite this into slope-intercept form so that we can graph it. So I'm going to say subtract x from both sides, and we get 3y is less than negative x plus 15. And now we're going to divide both sides by 3. Negative x divided by 3 plus 15 divided by 3. And that gives us y is less than. What do we get here for a slope? We need a number for a slope. Well, what is the number on top? This is a negative what for the coefficient of x? It's negative 1. So when you divide it by 3, you get negative 1 over 3. That's the coefficient, and that becomes your slope. And what about here? We divide by 3, we get 5. Okay? So all we have to do is we go up here to 5, we plot a point. Let me do it in red so you can see it a little better. Plot a point. And then from there, what do? We rise negative 1, run 3, just like the slope says, the negative 1/3 slope. You should be familiar with what negative slopes do. They drop as you go to the right. That should be just a general clue whether you've got it right or not. Okay. Now I'm going to draw the line, and I'm going to get rid of those points just to make it a cleaner. Okay, so that's what the line would look like if it said y equals. So we graph it as though it says, as though it's an equation. Now let's look at it. Here's the issue that we've got is, can we include the line? Well, you should be coming familiar with this at this point. Does it say or equals? No. So if we picked points on the line and we plugged the coordinates in, and by the way, let me see if I can erase the everything leading up to what we got as a solution to what we graphed. The reason that I'm taking this away is because I want to actually, when I pick a point and I test it, I want to test it into the original equation. You should always be plugging things into the original equation to test them and see if they work. Okay, so what do? Let's see. I'm going to write, well, I'm going to pick a point that's right on the line. Let's say this point seems to be right on the line right there. Let me put a point there. That point right there. What is that point? That point has the coordinates 3, 4. Okay, so we're going to test it. Hopefully you can predict what we're going to get. Let's try it. Where I have x, I'm going to put parentheses, plus 3. Where I have y, we're going to put parentheses, is less than 15. And I'm going to plug in 3 for x, 4 for y. And then we're going to simplify this out. Okay, we get 3 plus 12 is less than 15. Or 15 is less than 15. True? No, not true. 15 is not less than 15. 15 is equal to 15. And that's the crux of the whole thing. If we don't have or equals there, then when we plug in a point on the line, we're always going to get the same number on both sides, and equal to doesn't work. Some number is not less than itself, it's equal to itself. So if we don't have or equals, it won't work. So points on the line won't work, meaning we cannot include the line as part of our set of solutions. And then how do we visually make that look? Well, we've got to have a dotted line instead of a solid line. So I'm going to pause this. I'm going to draw a dotted line there, and I'm going to get rid of the solid red line because we can actually include that. Okay, so there's the dotted line. There's nothing special about where the lines, like how it's dotted. It's just the fact that it's dotted means you can't include anything on the line as part of the solution. So then what we want to do is look at this form right here, what we wrote here. It says y is less than. And so we need values less than. So what does that look like? That looks like everything below the line is going to be a solution. And if you want, as you can see, like I've been trying to point out, the point 0, 0, the origin, is really easy to test in there. So you can try that yourself and see, does it make a true statement when you plug it into the original thing. It's in the solution set. It's in the shaded region, so it should be true if we did it right.